Tom, nice to be with you here for this interview. We have some very interesting things to talk about. You've gained some new insights into the speed of light, things that were previously thought to be a constant, and it is probably still a constant in the idea or in the regards that it is still a constraint. However, this constant has been discovered to vary, and one of the people that have mentioned this is Rupert Sheldrake. He's discovered that there have been variances in history to the speed of light and also to gravity. This is a sort of cornerstone of the virtual reality constraints that you describe in your My Big Toe. What are the implications of these variances of the speed of light, and can you tell us how and why they could vary?
Yes, I did see that video. I believe it was a TED Talk where Rupert Sheldrake talks about the 10 different concepts or ideas or laws or the way physicists think that aren't really so much factual as they are belief. And he was taking the scientists to task that they had all these things that they believed, but they really didn't have any factual data to support it. And in many cases, there actually was physical data that contradicted it. So he brought these out, and when I listened to him, I agreed with him. I thought all of them were problem areas, and he had he basically was saying it correctly. But the one in particular referring to was the one about speed of light. And he said that the speed of light has been shown to change. Well, now there's a couple of things about that. You know, we use this word constant. We say the speed of light's a constant. And I've said many times, speed of light's a constant. And that my theory shows why the speed of light's a constant. But then I'm using the word constant, not as a precise word that means it's exactly the same to, 75 decimal places forever and ever and can never change. That's not, I'm saying it's constant because if you measured it today and you measured it tomorrow, you'd get the same value. It's constant in that sense. But it doesn't mean that it can't change, and it doesn't mean that it hasn't changed. But those changes would only happen very occasionally, and then it would be constant in between. It's sort of like we say that cruise control on a car keeps the speed of the car constant. Well, it doesn't really, but we use that word because we mean, in a practical way, it is constant. And that's the way I meant with the speed of light. For all practical purposes, the speed of light is a constant, but that doesn't mean this constant can't, be modified or can't be changed a little bit. And we're not talking about huge changes in it, but can't be modified a little bit one way or the other. Okay, well, how does that work? Why would this happen? Well, there are a couple of ways, and of course immediately physicists would say, well, of course it's not the same every time we measure it because there's measurement error. There's always error in our both our theory of the way we're measuring it and the actual tools and measurement devices themselves. No number is constant. There is no such thing as an experimental constant in that sense, because we only have accuracy to so many decimal places. You see, if we can measure the speed of light to, I don't know what, 10 decimal places or even 15 decimal places, well, that's magnificent. But that's not really constant, because constant you'd have to measure it to an infinite number of decimal places, and that's just theoretical and never will happen. So there are no constants in that sense. But that's not really what Rupert was talking about. He wasn't talking about measurement error, and I don't think he was talking about the fact that there really is no such thing as a constant as far as a measured value go, because we can't measure with infinite precision. Therefore, numbers change as we measure them. But they should only change within the plus or minus values of our error. We should understand our error. But a lot of times when physicists do these experiments, they're guessing. They're making assumptions about the errors. And sometimes they might be wrong in those assumptions. So sometimes they may make two measurements and get different errors or get differences in those two measurements that are outside the error bars. But if it's a small amount, then that's not really a big deal either. So that's kind of the one side. I think many of the physicists would say, well, that's true, but it's unfair. It's not really a problem. But that's not so. There really is good explanation for why this constant changes now and then. And it can get bigger and it can get smaller. And here's why. If you look at the velocity of light, and why is the velocity of light, the value that it is, and if you've listened to the Calgary talk that I give, or the talk that I gave in Spain, you will find I give a kind of a long explanation of why the speed of light is the value it is. Well, I'm going to give you a very short version of that here, and I won't have the graphics that I have there. So if this confuses anybody, go to the Calgary talk and get the more detailed version with the graphics. Well, here's how it works. A velocity is a distance per unit time. Okay, now in a virtual reality, the distance is the distance between pixels, if you will. But in volume, in a 3D reality, then these are really pixels of volume, not pixels of area. So we have the distance is the distance between pixels, and we call that the Planck length. Okay, and the time is the refresh rate. That's the delta t that I talk about in my book and other lectures, and I make it a capital DELTA -T, the delta t, which is the refresh rate on this virtual reality that we're in. All dynamic realities, or all dynamic simulations, let's put it that way, have an outer time loop. Every so many units of time, they're recalculated. That's the refresh rate, just like for your monitor. Your monitor has a smallest unit of area, which is a pixel. It has distance between pixels, and it has a refresh rate. For most monitors, it's either 60 or 120 times a second the screen gets refreshed. Our virtual reality is the same way. So if we take the distance between pixels, the Planck length, and we take the refresh rate of our virtual reality, delta t, and we divide those, that's the speed of light. So what does that mean? Why is that the case? Well, that speed says how quickly can I move information from one pixel to the next. So that if I have information in pixel 1, in one delta t, which is the very next unit of time, I can only move it to pixel 2. And the next delta t, I can only move it to pixel 3. And you see, so information can move through this virtual reality from pixel to pixel to pixel to pixel. Every delta t, it can move one pixel. So this distance between pixels divided by the delta t turns out to be the speed at which information can travel through the reality frame, through the virtual reality. Well, that's the speed of light. Now, how could it change? Well, think of any simulation that you might have. In this simulation, why do you pick a delta t that you pick? Why would anybody pick a particular delta t for simulation? Well, it depends on how fast the action is in that simulation. If you have things in that simulation that move very quickly, then you need a smaller delta t, otherwise that motion will be jerky. It won't be smooth. It won't look like a movie, you see. So you need a higher delta t if there are time measurements that need to be more precise. And what about the pixel size? Well, you need to have a resolution in this virtual reality such that people in it and their instruments and the things that they measure see their reality as continuous. There are frames per second that go by, and when the frames go by that fast, we see the action on that movie as continuous. We don't see it as a bunch of individual pictures. But if instead of, 30 frames per second, it only went by at 5 frames per second, then the motion would be very jerky. Things would jump. It would seem like, motion would be like people teleport from spot to spot to spot, as as time goes on. The motion's jerky. So the measure of the delta t and the, we might call delta x, which is the distance between pixels, is picked based on the computer resource requirements. So if you have a computer resource requirement for a certain resolution, you see, then that resolution says we have this many pixels per unit volume, then you need more throughput if you have more pixels. Okay? Every pixel is a certain amount of data you have to keep track of. So higher resolution requires more data, more throughput in your simulation. And if you have a faster delta t, then you're getting more data out, you see, per unit time. So it's basically the size of the processor, the amount of data you have to process, and the speed with which you have to process that data. That's why so it's those factors have to match with the resolution, both in time and in space, that you require in the virtual reality. So that's kind of the whole picture of what C is, why it's a constant, and how it can be changed. So why would it be a constant? Well, if you've ever done simulations, you wouldn't want the time, the delta t, to change very often. You only change it when you need to. You spec it based on your resources and on the requirements of your simulation. If those requirements change, then you might change the delta t. But you don't just change the delta t around all the time, because what that would do, it would make your time progress in your simulation not constant. You see, your simulation progresses in its time by these delta t's, and it would be like if you were watching a movie and sometimes it was running at 30 frames per second and sometimes at 60 frames per second, which means everybody would be going very fast, it'd be like a fast forward, and sometimes it's only moving at 10 frames per second, and that would be slow motion. So you jump back and forth between slow motion, regular motion, and fast motion all the time in this reality. So that would be really crazy. It wouldn't be the buttoned down, reliable reality that we need in order to get good feedback from our choices. So we want a reality that's smooth and looks continuous. And it's the same with the delta V's, the deltas in the volume, because if they changed, then it would be like on your screen if your pixel size changed. If part of your screen had, sometimes you had a very high resolution and sometimes you had a very low resolution, what you saw would change all the time. And from minute to minute, you wouldn't have consistency in your reality. So that's why C is a constant, because we need this constant homogeneous reality frame in which to lower the entropy of our consciousness. It won't do for this reality frame to be goofy and jumping around and teleporting and sometimes grainy and sometimes not. So that's the point of it being a constant. But now let's say things change. When we have things that are very slow, which take the last 10,000 years up to maybe 100 years ago, well, there weren't things that were very fast. About the fastest thing going was maybe birds flying. Some birds get to like 60 miles an hour, but horses don't run that fast. People don't run that fast. Hardly anything went that fast. So the speeds that were really fast in this reality were far and few between. We had lightning maybe that was fast. You could see flashes of lightning and things like that were fast. But there wasn't a lot of fast stuff that you could study really up close. Lightning flashes, that kind of thing, I guess would be the fastest thing that we'd have. But now, look at us. We're measuring things down into the nanosecond in time, okay? And we are smashing atoms apart, looking at tiny little things that live for only, 1/30th, times 10 to the minus 30 seconds, and things like that. So we're dealing now in very small times and some very fast things. We have, we fly missiles now at rockets at Mach 6, Mach 10, things like that. So suddenly the requirements in the simulation are going up as our technology gets more and more sophisticated. So you can see that perhaps the system might want to change its values of delta t and or delta x, the volume. I say delta x. X is a distance, and we're really talking about, kind of a delta v, but delta v, take the cube root of delta v and you get a delta x, like the Planck length. So you can see that the system might want to change that because resolution requirements are getting higher. Now what they would try to do is keep the ratio delta x to delta t, which defines velocity, x over t, distance over time. They'd like to keep that ratio about the same, because otherwise the scientist here would go, hey, the velocity of light just changed, a lot. If all they did was change the delta x, which then mean that the light speed would get faster, or if they just changed the delta t, let's say they made delta t smaller, then light speed would get faster. They made the delta v or the delta x smaller, higher resolution, then the light speed would get slower. So what would they do? They'd want to keep it the same so that our reality stayed about the same, right? So they would try to change it so the ratio was about the same, but they can't do that exactly. Why not? Because they're digital. You can't change them in a continuous way. You can only change the resolution by certain, quanta. You can't just change it. You can't twiddle in the 23rd decimal place or something to make the ratio come out just right. It's got to change by a whole unit. In other words, your delta t's are integer numbers. There's only certain numbers of delta t. You can't have a half a delta t. See my point? You can't have a half a pixel. Pixels come in whole integer numbers, and so do delta t's. There's integer numbers of those things, not half pixels and half delta t's. So you have to make this arrangement so that you move both, so that you would say if you decrease the delta x, then you'd want to decrease the delta t by exactly the same amount, is what I'm saying. That would keep the ratio, the speed of light, the same. But you can't do that exactly because they're digital. They're quantized. You can't have pieces of pixels and pieces of delta t's. So they kind of jiggle that the best they can, but one should expect some differences. It could go up, it could go down a little. Now, if they decided to actually let that ratio change, they could really change the speed of light. The speed of light could change dramatically if they kept the delta x the same, the distance between pixels, and then dramatically reduced the size of the delta t. In other words, the frequency on refresh goes up. Then suddenly, if you have a reduced delta t, but the x stays the same, you're making that delta t smaller. Well, you divide the same numerator by a smaller denominator, you're going to get a bigger number. The speed of light would go up, you see? And it could go up dramatically. It could go up, orders of magnitude. But we haven't seen anything like that yet. All we've seen is just little things, which probably means that once our technology got good enough that we were starting to make very refined measurements, or maybe just because there was some reason in the way that things are calculated, in the rendering engine. We talk about a virtual rendering engine. There's certain things that have to go on, processes that are doing the rendering, and those may just change a little bit now and again. Things aren't perfect. Computers don't, can't but be so accurate. Computers have their own limitations on how many decimal places they want to compute. In a computer, it's either single precision, and that's like 8 significant figures, and double, that's like double precision, 16 figures. But every time you go up and ask for more accuracy, it costs you more, more information has to be processed. You have larger and larger bytes. It takes more computer power to do that. So there's all these trades.
Were they asking for more accuracy when they were searching for the Higgs boson particle? Can you explain the implications of that discovery in terms of
Well, yeah, that's a little different
laws?
subject, but we can kind of put that in here. Yes, they were looking for events. The Higgs particle only exists for a very, very small amount of time. It's not a particle that everybody can kind of sit back and watch go by. It's an event that I think it may be something like 10 to the minus 35 seconds or somewhere in that range of time that this Higgs particle exists. Okay, so it is an extremely short-lived experience, but we're seeing things that basically events that are that short, that small. Now that may drive the delta t to be a little smaller, but now I've said that our delta t is like 10 to the minus 44 seconds, so that's small enough for us to see, a Higgs particle. So there really wouldn't be necessary to change it by very much. But what it would say is that we're starting to press the limit of how the virtual reality is generated. When we start doing things like measuring Higgs particles and in this big accelerator, we're starting to push the limit of what the simulation is able to simulate. 10 to the minus 30, say 34. Let's just make a number. And 10 to the minus 44. Well, that's still quite a there's quite a distance there, but we're beginning to press that limit. So yes, when things like that happen, I can see that the simulation mechanics, that those running the simulation, are beginning to see that perhaps there's a need to make some changes. So we are pressing things.
Rupert Sheldrake had said that between 1928, what he discovered in his research, between 1928 and 1945, there was a drop in the speed of light of 20 kilometers per second. Can you present a hypothesis on why that would have happened in that time frame?
Well, there's maybe a couple of reasons. If that was at the time frame, see, the early 1900s, I don't know what we say about 1920 up through the 1940s, that was when quantum mechanics was birthed and generated. That's when quantum mechanics started its life and went through its adolescence and kind of grew up during that period. So if we go to 1920, 23, 24, in that, the early 20s, maybe the late teens, I'm not sure of exactly when one would pinpoint when it started, but early 1920s through the 1940s, it was when most of that early quantum mechanics research was being done and quantum mechanics was invented and turned into a science right during that time. Okay, so that was one event, major event in science that was taking place then. Now, whether that would be a reason for the larger consciousness system to want to meddle a little bit with the ability of the simulation to simulate, that would have been the right handwriting on the wall that said, hey, before long, we're going to be pressing the limits here. So perhaps that might have been a kind of a reason for that to change, or it may be something else. It may just have been a little adjustment. You try to when you're running a computer simulation, you're always balancing how small can you run delta t, how small a delta t, which means how much resolution can you afford? Because again, every time you make that smaller and your resolution gets bigger, there's more data to process. It may have been that the larger consciousness system found a more efficient way to process the data, which meant that it could decrease the delta t, make our resolution a little better because it had a little better technology. It could be something like that as well. When I was first running simulations back in the early 1970s, the computers were so slow that it would take months to get a single, computation done. I'd set up my problems and the computer would work on them for 2 months and produce just a number. And of course, I had to be very, very careful not to make my delta t in that simulation any smaller than it absolutely had to be. Because if I made it, too small, I might wait 3 months for an answer. So it could be just a matter of the larger consciousness system finds a more efficient way, gets a little more resources, puts a little more resources to this problem. So there's any number of reasons why this might change, why the larger consciousness system might modify, its delta t or its delta v, its pixel of volume. It doesn't have to be because we're forcing it to do so, but we are beginning to do that. So we expect changes in the speed of light, but that doesn't mean that the speed of light isn't a constant in the practical sense of the word. It's constant. From day to day, month to month, year to year, speed of light's a constant because you keep the simulation running at a constant, as close to a constant as you can, so that your action is smooth and the same from time to time, etc. You change it when you have to, when there's a reason. So that's why we call it a constant, even though this constant might change now and again. Now, there's another interesting thing about this. There's some other reasons why this speed of light might be the value that it is. The speed of light may be the bars in our playpen. It may be the constraints. And by that I mean, we talk about, in Star Wars, they go warp speeds, and that means they go faster than the speed of light. That's what warp means, faster than speed of light. And everybody figures that, well, someday we'll go faster than the speed of light, and then we'll be able to travel to the various, galaxies and stars and yada, yada, yada. And that's kind of the dream. And everybody expects, sure, that'll happen one day. But that's because we watch so much television. That's why we believe in that. We think that, of course, we'll do that. Well, that's not so likely to happen unless, we have a different speed of light. And the reason I say that is that even the very closest star to us, Alpha Centauri, is, I believe, 4.5 light years away. That's the closest. Okay, now there's billions and billions of billions of stars, in our universe. And the very closest one to us is 4.5 light years. Now, Einstein, in his relativity theory, says matter cannot travel as fast as the speed of light. Matter will always travel equal to or less than, well, not even equal to. At equal to, there's a singularity and the equations blow up. So it always has to travel less than the speed of light. So if we get out to a place in our universe where it's interesting, where there are maybe planets like ours or maybe other potential life forms, etc., we're talking now of going hundreds, if not hundreds of thousands of light years out into space. And that's just a one-way trip. If it takes you, 100,000 light years to get there, it'll take you another 100,000 light years, to send a signal back. And that's traveling at the speed of light. And if your mass, like our spaceships are and like we are, then we have to go less than that. Now imagine on our planet with our societies and our people that we're going to have an adventure. We're going to make a scientific adventure. We're going to send off the people to see, like they sent off, Magellan and Columbus, to see whether or not the world was flat or round, right? Go sail and keep going and see where you end up. Well, that might have taken months, maybe even taken half a year, or maybe even a year or so, before those people come back and report. But what if it took 50,000 years? Can you imagine? I mean, look at our history. What was going on 50,000 years ago? We were dragging our knuckles on the ground, right? Chasing things with clubs. What differences are you going to find now that technology and things move faster, in another 50,000 years? And that means it's only 25,000 light years away from us. It's 25,000 out, 25,000 back. Well, 25,000 light years away from us is sort of like in our own backyard. That's not very far. That's, that's hardly, going out there and really looking much. We're liable not to find much that close to home. We're liable to have to go much further than that. So the point is, in practical terms, this space travel, going out to other planets and other galaxies and so on, is just not practical unless you can beat the speed of light and go much, much faster than the speed of light. And Einstein says you can't do that. Now they've thought of wormholes and other things, ways that we can trick space and that kind of thing, but that's really as much science fiction yet as science. It's a possibility, but it's way out there on the fringe of possibility. So don't count on wormholes. So we're kind of locked in here. We can't really go out and explore space except in our very close neighborhood. We can't do experiments that take 50,000 years or 100,000 years or 200,000 years before the result of the experiment comes in. By that time, nobody left on the planet would even know that the experiment existed. There's too much entropy in the system for that. So that's a very practical problem. We're kind of stuck just getting around. If we can get out even in our solar system, that's pretty good. And to get out to the very nearest star, which we can probably tell doesn't have any planets going around it, you see, that's 4.5 years out, 4.5 years back. So that's 9 years before we'd know about that. We don't have attention spans that are much longer, than maybe 20 or 30 years, but hundreds of years. 20, 30 generations go by before, your explorers out there can send a light signal home. Whether they made it or what they found out, thousands of years go by. No, it just doesn't make any sense, does it? So that's a problem. But this light speed, as we said, could change. So I think perhaps, in one of my talks in Dublin, I talked about how if you see the pattern of how we have developed here, of how life has developed here on this planet, we see that it develops, it works this way. It starts off and there's maybe a one-celled thing. And that one-celled thing splits into two different one-celled things. And now maybe there's 10, now maybe there's 10,000 of these one-celled things. Well, that's an advantage. They can lower their entropy some because now they can interact with each other. That allows a lower entropy. But what's their mission? What is it that they're supposed to do? Well, evolutionary mission is to cooperate, to work together. Eventually, some of those one-celled things cooperate and work together enough that they form a multi-celled thing. Now they have a thing that has multiple cells because the multiple cells, let's say the multiple pieces of bacteria, are now working together as one unit. They're cooperating. All right, then what happens? Well, you have multi-celled things, and those multi-celled things, they split, and now you have lots of multi-celled things. And that lowers their entropy. But what's their mission? How can they lower their entropy even more? Remember, lowering entropy is the way you evolve. That's the way physical things evolve as well as the way consciousness evolves. Well, these lower entropy, multiple-celled things, they get together in what we call cell differentiation. So then they're now working as a one bigger thing. You see, they kind of belong to the one thing. And now they have organs. They have specializations of cells. This is the motion part. This is the breathing part. This is the digestion part. You see, this is the fighting part. So they have all these various parts. And each one of those parts is like a multi-celled, organism itself. So now they have one big thing. Now, those things evolve to become bigger and more complex by lowering their entropy. And what do you end up with? Us. We're one of those multi-celled things with differentiated functions in our cells. And what is our mission? Our mission is to be cooperative. So cooperation comes with things like balance and compassion. You can't have cooperation if you don't have these other things. So we need to cooperate to become one bigger thing. And that doesn't mean that we lose our individuality. We still have our individuality. We're just part of something bigger. And it doesn't mean that we lose our freedom by being part of something bigger. We gain freedom. We have more options. Our decision space grows, not shrinks, as we become one of something bigger. Okay? What's an example of that? Well, look at look at cities, the rise of culture. What happens? Well, people came together and they built cities. And in those cities, there was specialization of function. You had the cobbler, you had the blacksmith, You had the warriors who protected. You have all these things. You had the farmers. And because of that, everybody didn't have to be a cobbler, be a blacksmith, be a warrior. People could specialize. And what did they find? Well, the cities were so much more efficient, so much more effective. You had so many more opportunities in a city. It's the same way. When you cooperate together, it doesn't mean you become a slave to the larger organism. It means you get a bigger decision space. You have more choices, not fewer. People have this mindset that, oh no, we're supposed to become a one thing. That means we'll all become cogs in a bigger wheel and we'll lose our freedom and our individuality. No, you gain greater freedom, greater individuality, more choices, larger decision space, lower entropy, you see. So what's our mission now here as these human beings? Well, we are to cooperate. We've done it some in cities. We do it in, say, corporations. We do it economically. We have places where we cooperate, and we find it's very efficient. It lowers entropy. But what about with each other? We humans, we learn to cooperate with all the rest of the critters and beings on this planet, with the inanimate objects too. In other words, we kind of respect the ecology, the biome, that is our, this planet Earth is our biome for human beings. So becoming one with the whole planet, with each other, makes us more free, and we become one thing. And then once we do that, and we've kind of gotten that act together, then what would be next? Well, let's step up the ladder, and let's say next would be to interact with other units like ours, right? Just like the bacteria interact with other bacteria. And where would they be? Probably other planets in the universe, other things, other places. Well, then we'd want to organize at that level instead of fighting each other. Oh, we're going to fight the people from, whatever, the aliens and fear and get into that. We need to get over that and be cooperative at a galactical level, perhaps. Well, we can't do that now. Why not? Because we can't travel fast enough to make that a practical reality. Why not? Because our speed of light is so slow. Do you see now why I say that the speed of light may be the bars in our playpen? Until we evolve to the point that we have gotten rid of enough fear and gained enough quality in our consciousness, we have no business out there, interacting with other, entities from other planets, other places in this universe. We can't even interact successfully with ourselves, you see? So why would we want to be let loose on the next bigger level of organization when we have not mastered the level of organization that we're in? You see? So that kind of says, well, maybe it's a bigger game than we thought. Maybe when we grow up to the point that we have evolved enough, the larger consciousness system will say, okay, guys, I'm going to let you get out of your playpen. All I have to do is decrease delta T by 3 orders of magnitude. And I can do that. I've got the computer power to do that. So I'll decrease delta T by 3 orders of magnitude, and guess what? Speed of light just got 1,000 times faster. Now what was 1,000 light years away, it's only 1 light year away. We move in 3 decimal places, right? Or more, it doesn't matter. So now let's look at the universe. And we're not an old solar system. Our solar system, our planet, is not like the first one that existed. We are billions of years after other such places probably existed. So there are other solar systems, other places in this universe that are much, much billion years older than we are. Well, where are we going to be a billion years from now? I suspect we'll be quite a bit further along than where we are now. At least I would hope so. So where are these people that should have so much, should be so much more advanced than we are because they've had an extra billion years to work on the problem? Well, maybe, none of them existed. Maybe there's only some that just are a million years ahead of us. Well, even a million years, even 1,000 years ahead of us is a huge is a huge gap. Maybe we were just particularly quick and we caught on fast and, we've evolved very quickly and others are evolving slowly. Maybe. But there's a good probability that there are other life forms, other planets such as ours and other solar systems such as ours out in this fantastically large universe with its billions of suns. Okay, so the probability that the other arrangements that are similar to ours that would support life is high, even if it's only one in a 100 million. That means there's thousands and thousands of them out there. You see, so where are they? Well, we're still in the playpen. We're still in the playpen where light speed is the bars on our playpen. But now, there's no reason why everybody has to fly at the same speed. If you have a simulation, you can have parts of it going at different clock rates. And in my book, I give an example of that. So you have a simulation, and I give the example of a war game. So you have part of that war game is simulating the soldiers on the ground. Well, a soldier doesn't run more than a few miles per hour, right? Particularly with a big pack and big weapons and things. So you don't have to go very fast there. You can even have the hair on their arm moving and it still doesn't move very fast. Now they fire a bullet and that moves pretty fast, but it's not all that fast. It's not really that fast when you talk about light speeds. Bullets are still pretty slow things. But you might have a missile. And that missile may be going, Mach 6. And if you have a missile going Mach 6, now that's a lot faster than a bullet. So you might want to have that part of the simulation go in smaller delta t's. And the way that works is that you have subroutines that basically count the faster delta t's. And they say every 1,000 of the time loops, I'm going to take one increment in this slow time loop. So you can have time loops within time loops. It's not that hard to do in a simulation. So you have the outer loop, which is the fastest one, but inner loops can only increment n numbers of the outer increments. You see what I mean? So you might wait for 1,000 of the faster times to go by before the inner loop increments once. So that means it's not a problem with having different speeds of light for different civilizations, you could say, within the universe. There may be other parts of the universe where the playpen bars have come off and their speed of light isn't the same as our speed of light, because this is a simulation, and in a digital simulation, you can do all kinds of neat tricks that you can't do anywhere else. So that's why this is a possibility. So that then makes this thing about, I saw a spacecraft fly by the other day and, it was a real spacecraft and it just blinked out, and obviously they know how to do warp speed, but we don't. Well, it may just be that they, in their loops in which they live, which can overlap with us, there's no reason the two can't overlap. The soldiers on the ground are still playing in the same war as where the missile's flying in that same theater. There's no reason why they can't overlap in a digital simulation. So that's kind of a fun thing. Now, of course, this is all just conjecture. I'm not saying any of this exists or any of it actually works this way. I'm just saying it's possible. These are the possibilities in a digital simulation. And it looks like our light speed may just be keeping us here until we get a lot more grown up than we are. But if you look at this evolutionary fractal process, you see at every level in this process fractal that what you have is a group of individuals all on about the same level interacting. They have to learn. They have to grow up enough to cooperate. They have to have the caring, the compassion, the interest in cooperation. They have to not have the fear of each other. They have to have the trust of cooperation. You see, they have to grow. So as they become more love-like and less fear-like, they learn to cooperate. When they do, they get a larger decision space, more freedom, more decisions, bigger reality, more functional, less entropy, and then you start it all over again. Then those things you see split, and you have a bunch of those, and then those have to learn to cooperate. Then those things split. You see what I mean? It just keeps going up from the single cell all the way up to where we are, and we can kind of see that our mission now is to get over our fear-based, ego-based, belief-based, approach to life, become cooperative, become more free, become happier, become more productive. And when we have that as a planet, when all humanity has done that, which it's not just humanity, it's not like we're the only people, we're the only entities that count. It's all the life forms on this planet and all the inanimate stuff on this planet. You can't just, use up all the oil and then kill each other, over what's left. It's being, I don't know, what do they call it? Good, I guess the word is being, a good citizen and a good, husbandry, right? Taking care of everything so that it all works fine together. Good ecology, good sense, a good citizen, a good cooperative member of the planet and everything and every entity on the planet. Well, that's our challenge. We need to be able to do that. And when we do, well, I don't know that it'll happen, but at least it's a possibility that the bars will come off of the playpen. That may be how we get out into space. We may have to wait until we earn that right to go out and mix up with the others that are more advanced than we are, been around longer than we are. And until that, we're kind of in isolation. That's what children in a playpen are. They're kind of isolated to keep them out of trouble, keep them from hurting themselves, keep them from hurting others, keep them from playing with knives, right? Running with scissors, whatever toddlers might do, get in, pull everything out of the drawer, and just because they like to hear it hit the floor. It's to keep them out of trouble. Well, maybe that's where we are. Maybe we're being kept out of trouble at this point, and that it's not a given that we're going to learn to sneak through a wormhole and just going to have to observe Albert Einstein's, speed limit when we grow up. That is a possibility. I'm just talking about what's possible here, bigger pictures, things that may be, but they may not be this way. We don't know. We won't know till we get there how all this works out, but it's just fun to think about the limitations and lack thereof. What are the possibilities here? So that's what we're doing. We're just kind of roaming over some of the possibilities, and I think it's interesting, and at least it's fun to think about how this might work.
That is very interesting, and it certainly makes sense. If the next evolutionary step for mankind is cooperation, I wonder how we're doing so far. One of
if you want to know how we're doing, go watch the news.
Yes.
Go watch the news and read the paper and see all the stories about how people are cooperating and caring for each other, how they're trying to help each other out. I mean, we are some, but it's we have quite a ways to go before that is a good description of humanity and our interaction with everything else on the planet.
That's right. One of the other dogmas or beliefs of science, material scientists don't seem to recognize consciousness. And I know that others have alluded to it. Edward Fredkin says the answers exist in other. Consciousness seems to be the drawback to scientists trying to understand reality. Will we ever break through that?
Well, it's a belief. Even if you talk to consciousness researchers, go pick your top 50 consciousness researchers, okay? And these are the people that should know about consciousness. And they will tell you that there's this thing called the hard problem in consciousness. And what the hard problem is, and this is the big thing that they can't solve. They can make a lot of progress everywhere else, but they just can't solve the hard problem. And what is this hard problem? It's how do you get awareness? How do you get consciousness out of basically inanimate matter? Okay, the brain is just a bunch of cells and electrical impulses and that sort of thing. So how does one get consciousness out of a glop of inanimate matter? That's the hard problem. Well, the reason that that's a hard problem is that it doesn't work that way. You know, that's like saying, the hard problem is, how did you get all this water that's on our planet out of the stones? Well, it didn't come out of the stones. That's why it's such a hard problem is, how did all this water materialize out of the inner core of molten stone, molten iron? How did that happen? Well, they're thinking of it wrong. The water didn't come out of the molten core. That's not the way it works. Well, that's why this problem in consciousness is such a hard problem, because consciousness doesn't come out of a brain. You see, the brain is a virtual brain. It doesn't produce consciousness. But yet even the consciousness researchers, they believe that consciousness must come out of the brain. The brain somehow creates it. But every time they try to come up with some theory or idea of how can the brain create consciousness, they fail. And because they don't see any way forward, they always fail. They call it the hard problem of consciousness. Well, it is a hard problem, just like trying to figure out why or how water pours out of stones. It's a hard problem. You see, it doesn't come out of stones. It comes out of underground streams that run between the stones, you see. So they're just missing the point. They will never find out how consciousness is generated by a brain, because consciousness is not generated by the brain. The problem is hard because they don't they're missing the whole idea about consciousness versus matter. But in their minds, and in the minds of scientists in general, they believe that physical reality is all the reality there is, and that everything that's here is somehow taken back to a physical cause. That's the physical causality. So consciousness is obviously here. We are conscious. We know that. So it's a fact, and we want to somehow trace the causality of that consciousness back to a physical cause. And of course, it's the hard problem because it just doesn't work that way. So you say, will they ever get over it? Well, you'd think if they were more logical, they'd say that, well, we can't find any way that that's possible. And if that doesn't seem to be possible, maybe we need to look for another explanation, as opposed to keep trying to beat this already dead horse that will never get up and run again, but we just keep beating it and beating it. And we say it's a hard problem getting this dead horse to get up and run again, and we just don't know, but we'll keep beating it and see what happens. You see, well, eventually you kind of have to say, well, maybe we're just, beating a dead horse and it isn't going to happen. We need to think of some other way. Consciousness doesn't come from inanimate matter. Perhaps it's the other way around. Perhaps inanimate matter comes from consciousness. Let's try a different approach, but they don't, because they believe so strongly that everything must have a physical matter causality that they only say, well, okay, the horse is dead and we keep beating it because we keep expecting it to get up and run, but we're just not beating it hard enough. We're not beating it with the right whip. If we just found a better whip or could hit it a little harder, maybe it would get up and run. But they don't. They just, they don't see the problem there. So the idea is that we know it must come from physical cause, but we just don't know how, and that's the hard problem. So I don't know when they will get over it. They'll just have to get over that belief. Right now, it's going to be no time soon, because that is the core belief. Talk about, Rupert Sheldrake saying that science is belief-based, and he brings up these 10 areas where they're obviously just scientific beliefs and not facts at all. Well, that's one of the main beliefs, is that everything must have a physical cause. And for most of the things here that are pieces of the simulation, they do, because there is a rule set, and the rule set is why we have physical causality. But when it comes to consciousness, that's a different thing altogether. And it just is a belief like any other, like any religious belief, like any kind of belief. How do people get over things that they truly believe in? It's a slow process.
He also said science can't deal with the fact that we are conscious. And you have said that basically this computer simulation that you are using as a model for your reality, the consciousness is the computer. That's where the scientists are failing to realize.
Yes, all sorts of scientists now have jumped on the bandwagon about reality being virtual. I even watched a talk, a month or so ago, and actually it happened last year in 2012. There was a conference, and the subject of this conference was virtual reality, and they had this panel of 5, high-powered physicists, top in their field, and they were all saying, yes, reality is information. This is a virtual reality. So the idea that scientists now are beginning to see that virtual reality is better physics, that's come along, that's been accepted so much in the physics community that 5, high-powered physicists, from the likes of MIT and other, places like that, sit down and talk seriously about it. Whereas when I first published my book a decade ago, you couldn't have found anybody willing to, stand up in public and say that reality was virtual. They would have been, shouted down by their peers. But now here's the whole panel of them, and they're all talking about this, and it's a very serious accepted subject. So we've come a long way there. Virtual reality is being accepted. But what they can't get their minds around is that a virtual reality has to be computed elsewhere. A simulation does not compute itself. You have to have a computer, and the computer creates a simulation. But the simulation has to be computed. It can't compute itself. So Fredkin understood that, and he said the simulation, can't compute itself. It has to be computed elsewhere, and he called elsewhere other. But the thing so he gets it, and some of the other physicists get it, but most are still, it's that same belief, you see. They say, well, but if it's computed elsewhere, then that means there's something other than this physical reality. No, can't go there. No, can't happen. This is the one case where the simulation programs and computes itself, and of course that's illogical. That's like the camera taking a picture of itself. If you're the thing taking the picture, then you have to take the picture of something else. The thing that takes the picture can't take the picture of itself. This is like third grade logic, but there were at least 3 of the 5 physicists on that panel just couldn't go there, that it had to happen in other. They go, no, I can't understand it, but I can't go there with you, Dr. Fredkin. So you have you run up against this belief that physical reality is all there is, and everything has to be derived from this physical reality. So, okay, there's this virtual reality, and obviously logical tells you the simulation has to be computed elsewhere. But no, this is a special case where magic happens, and that doesn't apply. But anyway, the point is that virtual reality is becoming acceptable physics. It's even starting to dominate now because it's just the truth. It's so much better physics. The truth isn't fragile. Eventually people have to face up to it. But the idea that consciousness is the computer, that is not even on the boards yet. That's not even a minor blip anywhere. Dr. Fredkin doesn't even go that far. He just says other. And he will, he can't take the step consciousness is the computer, because that's a big step, and scientists don't want to go there either. They would find it easier to say, well, there's some other universe it's physical just like us and has people in it that look just like us, and they've created the simulation, and we're in their simulation, but we're just a subset universe of a bigger unit. They can make all this stuff up, but they can't get to the point that there's something that is other than physical, and that physical and non-physical are just a point of view. I call that the next level up of the theory of relativity. The next up level, in relativity, it's, there's no unique inertial frame. All inertial frames are the same. They're just relative to each other. Well, there's no there's no fundamental inertial frame. Well, there's no fundamental reality frame. Reality frames, are just relative to the observer. So this idea that there is a non-physical reality that just scares scientists so much because they don't understand like this next concept up of relativity. That doesn't mean anything. Your dream reality is non-physical. When you're in that dream reality, this reality is non-physical. What's non-physical is just depends on where you are, what the observer is. So here we are in this universe, and this universe seems physical to us, but there are other places outside this universe that seem non-physical to us, but to the people there, they're physical and we're not. See, so this idea of, non-physical, that's woo-woo stuff. If it's non-physical, then you do a little Twilight Zone music, and that's only for people with weak minds. But it's just another higher level way of looking at reality. There's lots of reality frames, and each one, the individuals who are playing in that frame, their frame is physical, and the frame that we're in is not. So it's not such a big deal of the woo-woo spooky non-physical. It's just another frame of reference. That's all. Just like in Einstein's relativity, the fact that time slows down and mass increases and all the special, the effects of special relativity. It's just it's just a perception from a particular frame of reference. When you're in that rocket ship going 0.9 the speed of light, you don't feel like your time slowed down. You don't feel like mass has gotten bigger. It's only the people who are in a different reality frame at a different velocity than you who measure those effects. You see, so it's just the point of view of the individual. But so anyway, this works the same thing, and it's nothing that scientists should be so terrified of. But they are, because this non-physical has been associated with the spirit world and the mediums and that sort of thing. So they feel that that's already been described as woo-woo and unbelievable and non-credible. So they can't let themselves think beyond that label that they have put to this, because they didn't really understand where it comes from.
Well, that is another one of Dr. Sheldrake's points of scientific dogma. He calls it science as a method of inquiry versus science as a worldview or the belief system. And one of his points, the 9th one, is psychic phenomena is illusory. Despite all of the evidence to the contrary, it's still overlooked.
Oh, yes. I mean, go and Google Pear Labs. And Pear Labs has for decades been doing experiments where people modify random number generators and random events with their minds. So that's sort of the mind over matter. That's consciousness affecting this reality. It's been done, hundreds and hundreds of times. It's been done by qualified, PhD scientists. The way they do it, their protocols are immaculate. They're very good at tracking their errors. They know it's real. And on their website, they'll tell you that the statistics that make them, credible. You have these statistics that you have to get a certain value in your statistics that makes it seem like it's real as opposed to chance. It's called significance in statistics. Well, their significance value that their data could have just been gotten by chance, okay, is less than 1 in a billion. Nobody has statistics that good, on research. 1 in a billion, that it's random. So these are real events, and everybody just looks at it and turns their head the other way because it conflicts with their belief. No, that can't happen. It's their belief. Yet we as a society, we accept that. We accept it so much that it's law. If drugs don't perform better than the placebo, there is a side effect that's part of our law. Our society, regulates drugs by a side effect. What do you mean there are no such thing as side effects? Gee, they've even made it into our law. Because how should that happen? Why does it matter to this deterministic physical body, no matter what you tell it? You could tell it anything. It's just a matter of biology. You swallow a medicine, and the medicine either fixes the problem or it doesn't. the medicine goes into the body and, it does what it does. And if it doesn't fix the problem, it doesn't get better. If it does fix the problem, it does get better. What you happen to tell the person and what they believe could have nothing to do with it. How could their perception, their belief affect, the disease on their liver? Well, that's a physical thing. Mind over matter. The mind can affect, the health of the body because of what it believes. Ridiculous. That couldn't happen, right? That's mind affecting matter. We know that's impossible. But yet, here's the placebo effect. And everybody says, oh, yeah, placebo effect. Yeah, that's good. That's sound. We have laws by it. So we even have psi effects that are part of our culture and part of our legal requirements. So, this idea that, the people at Pear Labs, they must be nuts. They think they can change probability distributions with their mind. We know mind can't affect things like that. Mind can't affect matter, but, so it's inconsistent. But then what I call true believers, that are people who are so completely captured by their belief that they can't think outside of that belief trap, that's what I call true believers. True believers don't mind a little inconsistency. They just ignore it and go on. No, the world has to be older than 7,000 years because, we can carbon date things way back further than that. No, I'm sorry. 7,000 years, Bible told me that. When you're a true believer, you don't care that there's information to the contrary. You just deny it and go on. Well, that's exactly what Rupert Sheldrake says science does. They just deny it and go on. And there's as much true believers as other people. And it's the same thing where they get tripped up all the time. So yeah, he's completely right. That's like the hard problem. Why don't they realize that dead horse is never going to get up and run, and go on and try something else? Because they believe that consciousness, because it's here, must be derived physically. It just seems to be impossible. Darn, it's just one of those hard problems, That's like, in quantum mechanics, those particles, they actually seem to be probability distributions. Well, just one of those things we'll never understand. Nobody will ever understand this. Let's just do the math and go on. It's the same thing. You have this belief that things have to have physical cause. Well, probability distributions aren't physical. What could they have to do with physical particles? How could a physical particle come out of a probability distribution? Just can't happen. So let's just say that nobody will ever understand it and go on, when there's a perfectly good reason for it. This is a statistical, probabilistic, virtual reality, and what exists here comes into existence, from probability distributions. What we measure is what we draw out of those probability distributions. Of course, they're probability distributions before they're particles. That's fundamentally the way the physics works. It's not a thing to deny and go on. It's a thing to embrace and go forward, just like the placebo effect. Okay, it works. Embrace it and go forward. Same with Pear Labs. Think about it, but Pear Labs, with all of their credentialed physicists, can't even get a paper published in a mainstream science journal, you see? But now this is Princeton. We're not talking about, lone rogue scientists with crazy ideas. We're talking about a buttoned-down Princeton, group of scientists. The Pear is Princeton Engineering Anomalies Research. Okay? Can't get papers published because they conflict with current scientific belief. And that's what Rupert Sheldrake is saying, and he's got that one, right on the nose. Scientists have these beliefs, and where they have beliefs, they're belief blinded and can't see what's obvious right in front of them. Psi doesn't exist. Okay, things, that goes all the way back to Duke University back in the, 60s and 70s. They were doing experiments that verified that psi does exist. Some people get very good at telling you what picture is going to come up next. There's been thousands of experiments that have had very good scientific credentials of the people and very good scientific protocols, and they just get ignored because they conflict with belief, just like the Pear Labs. So that's why the paranormal is treated that way, as it conflicts with scientific belief.
Of course, and another one of Dr. Sheldrake's points about scientific dogma is that the evolutionary process has no purpose or direction. And I know that's not what you've discovered. In fact, that's one of your assumptions.
Well, we assume that there is such a thing as evolution, that complex systems capable of change will change to better suit, their needs, better suit their environment. I mean, that's kind of what evolution is in a key. And it is open-ended. It's not a closed process. It continues on. Evolution doesn't have an endpoint. It's just change. Things change and modify in order to better suit, their circumstances. So that's evolution, and it's obviously, technology. Just look at technology as a system. Technology changes. It evolves. Our transistors wouldn't have occurred if we didn't have tubes, doing our electronics first. And our electronics wouldn't be unless we had what they were built on first. And the whole thing is just our technology evolves. So it's not just that humans evolved, it's not just a biological thing, but evolution is open-ended, and it evolves towards states of lower entropy. Basically, that's saying it evolves towards states that work better, things that, make you more functional, things that give you bigger decision space, things that enable you to, in the physical world, better survive and procreate. In the consciousness world, things that, just lower the entropy of your consciousness, things that move you toward love, away from fear. You see, that's the way evolution is. It's an open-ended process of change of a self-changing entity modifying itself to improve its situation. I mean, it's just very simple. And you say, well, how does technology modify itself? Doesn't it take people? Yes, but we're part of that system. We, the people that make the technology, are part of that system of technology. So yes, the technology does change, and it doesn't have reproduction and survival at its core. What does technology turn on? Well, it has to do with usability, demand, and functionality. What does it do? What kind of problems does it solve? What does it give us versus cost and other such things? Materials, costs, difficulty in making it, demand, all those things are parts of its environment that it has to improve on. Competition, you have all these other things. So evolution does have a purpose. It's to get better. And when it's not an aware thing that's changing, then it gets better kind of randomly. Then it's try everything, and what works best survives. What works best goes forward, and what doesn't work best doesn't go forward. It disappears. So in that case, it's not a choice by an aware entity. It's just a matter of the statistics. Everything that can happen eventually does happen, and if what happens gives you an advantage, then that tends to continue, and with what changes give you disadvantages, they tend to go away. So that's the way it is if you don't have an aware, chooser. But in things like technology and in things like consciousness, you have an awareness there that's in the loop. And when you still evolve the same way, it's just you don't have to try everything and what works, goes forward. You can actually think about what might work and where you want to go and try that first. And it makes your evolution a lot quicker that way. We have the standard model, it's called, quotes, standard model. That is the model. They call it like a standard model, like there's lots of other models and this one's standard. That's not the way it is. The standard model is the model in particle physics, and it basically says, here's all the particles and here's their properties, and it makes a nice little matrix that you can see how these things work. But that's another what does he say? Scientific dogma. The fact that the world is described in terms of particles is a scientific dogma. That's not necessary. That's a choice. You see, there's other ways that it could be described rather than in terms of these particles. We could describe it in terms of well, like they did earlier, particles and waves. There's some particles, some waves, but they kind of threw out the waves, and instead of talking about wavicles, which were something in between a particle and a wave, they decided to make everything a particle. But that's a choice. That's not necessarily because it's right. See, that's another dogma. It's a choice that's been made. So we have this standard model, but the standard model has two aspects to it. One of them is more or less accurate. The other one is more or less baloney. The one that's more or less accurate are the equations. The equations work. So the math works. And the standard model's equations are good equations. How we interpret those equations into physical meaningfulness, you have the equation, but then you have to interpret that. What does that mean? What does that equation mean in the physical world? Well, the meaning that physicists apply, the theory behind those equations, is just dogma. What happens is it's sort of like string theory. String theory has a problem that every time they run into an issue that doesn't work and they get stuff that isn't the way experiment says it is, well, they create another dimension to solve the problem. That's just like adding another assumption to solve the problem. You can solve any problem if you can make up enough assumptions to prop it up with. That's why we have this Occam's razor is a fundamental part of physics that says the fewer assumptions, the simpler it is, the more likely it is to be true. Because you can prop up anything with a lot of assumptions. Well, what happens in this standard model, in this particle theory, is they look at the experiment and they say, well, the experiment tells us this. So then they make something up to fit the experiment. You see? And then the experiment will tell them something else. Well, now they'll make something up to fit that experiment. And they've made all these things up to fit the experiments. Well, the equations are good, but their theory of making stuff up to fit the equations is not good. And here's a good example of that. Back before we got to Galileo, we had Ptolemy. And they plotted the various, stars and planets and things like that. But because they had a belief that the Earth was the center of the universe, we were it, right? God made us, made the Earth, so the rest of it would revolve around us. They had that belief that our Earth, our planet, was the center of the universe, and everything else traveled around us. So when they plotted these trajectories of the stars and other planets, they didn't get the nice picture that we get now when we say that the sun's the center. We have all the planets going around in nice little ellipses. They go around in nice little ellipses, and then the stars, they move relative to our sun and the galaxy and all the rest of that. But they then created the mathematics. They created equations that would do trace these things as if the Earth was the center. Well, now you can do that. You can take Newton's gravitational law, do a coordinate transformation. Instead of having the point of view, the center, the origin at the sun, you can put the origin at Earth. And then you just do a mathematical transformation. What do all the equations look like if the Earth were the center? And you can do that just as well. It's not simple anymore. Now you have the orbits of the stars and the planets. Instead of doing nice little ellipses, they're going up and down and then back up again, and they're making all these complex shapes. Well, you see, here's a case, and they called them epicycles because they weren't just cycles like normally we think of an ellipse, but they were epicycles. They were pieces of ellipses, but then they would break, and then another piece of ellipse. Well, what was going on there is that their measurements were correct. This is the way it appeared from Earth. And if you tracked it from Earth and plotted them, you got these funny little complex shapes called, epicycles. But their theory was wrong in the sense that it needed more assumptions. It was more complicated. It was more complex. So you looked at Occam's razor and you say, well, let's look at Newton's theory and then Kepler, and you see all of these just nice little ellipses traveling around the sun and the Earth's on one of them. Wow, that's so much simpler, you see? So we decide that we'll take that view. All views are the same. You can say the Earth's the center. You could say the moon's the center of the universe if you wanted to and calculate how everything else moves relative to the moon. You just have very complicated equations. Whereas when you put the sun in the center, everything falls out and it's nice and simple. So that's kind of the way physics is done. The fewer assumptions, the better. Well, the Standard Model is very much like this. They get the data, they make something up to fit the data. Their data's right, just like Ptolemy's data was right. But their theory, just like Ptolemy's theory, is not so good. It's just stuff they make up to suit the data. And so the Standard Model is really a lot of that, as Rupert Sheldrake says, is dogma. It's choice. You don't have to describe it that way. There's other ways to describe it that'll work just as well, just like describing everything as a particle. So they get in these odd things. Here's the problem. They create these things for themselves. And gravity is one of the problems. The Higgs particle is one of the problems. So their theory, of course, produces there's going to be a Higgs there. And they may indeed find a Higgs, or they may not. They found something they think might be the Higgs, but there's other particles that have very similar footprints, very similar fingerprints as the Higgs does. So it's not really sure that they found Higgs. That'll be years yet before they would know for sure. They're just claiming success because that's more fun than claiming failure. But actually, the jury's still out on that sort of thing. But what they claim then is that Higgs gives everything mass. Well, how can a little particle that lasts for 10 to the minus 36 seconds, give mass to the particle? Well, they say it's not this particle that does it. There's this Higgs field. This Higgs field is through all the universe. See, we're back to ether, like we were back in the Michelson and Morley times. We're back to ether. There's this Higgs field that's all through the universe, and everything has to move through this Higgs field. And the Higgs field's like molasses, and it slows you down, and therefore that's inertia. But there's more to mass than inertia. The inertia is just one characteristic of mass. You also have to deal with gravity. Mass has weight, if you will. It gets attracted. There's force also on this. So what have they done in order to make the theory fit is that they make up things like invisible, undetectable fields that are throughout the whole universe. Now, does that sound like science? There's this invisible, undetectable field that's throughout the whole universe that's like molasses. Right, guys? And I've seen these pink elephants that fly that nobody can see but me. You see, it's that sort of thing. They're invisible. These pink invisible elephants that are everywhere, but they're invisible so nobody can see them. It's like this Higgs field. It's everywhere. It's invisible. It can't be measured, and it provides mass to everything. Well, these are like the epicycles. These are people making things up to fit the equations. The equations are good. The measurements are good. And you do find this tiny little resonance, you would say, that makes a thing that looks like it might be a Higgs, but that's almost a trivial thing. There's tiny little, resonances might show up there, but it doesn't necessarily mean that it's this invisible field that nobody can see. But we just see these little pieces of particles will fly out of it, and that's what the Higgs is. It's just this little thing that kind of trips out of the top, and it only lasts a little bit. But believe me, there's this big invisible field that we can never sense or feel. Well, that's ether again. The reason we needed ether, the light needed some medium to travel on. You see, so we kind of come full circle back to these kind of magical things that nobody can see. Physicists for a long time had a problem with that action at a distance. How is it that a field can have force? This invisible field, can move things and have force. Well, the action at a distance didn't sit well with physicists for a long time, but since then they've learned to get over it. And now we can have all kinds of invisible things doing all sorts of things that nobody can measure, and that's the way it works. You say, well, I'm not saying they're wrong. I'm just saying that this is dogma. This is a choice. There are other choices they could make, but they're looking at the measured data, coming up with explanations, coming up with theory, and they've kind of gone down the wrong rabbit hole, it would be my opinion. And every time they come up with a new particle, that's basically a new assumption in their model. That's where I got started on this. It's a new assumption in their overall model of reality from the particles. So now if you look at all the particles, I've just read a paper, and some of the words I'm saying here I picked up from Brian Whitworth. He's in the process of publishing a new paper about the standard model. And so some of what I'm telling you I've picked up from Brian's paper. He hasn't published it yet. I got an advance copy. But it just fits here so very well. So here you have the same thing. There are other ways to approach this. And when you make stuff up and then believe it, that's what Rupert calls dogma. And he's right. So, maybe we could add an 11 and a 12 and a few other things to Rupert's model. And gravity is another one of them, you see. Gravity is another one. Well, if in the particle model, if everything's particles, then there's a gravity particle, and they call it the graviton. And it's got to be a boson, because that's the kind of particles it would fall into. And how does this boson, how does this gravity particle warp the fabric of space-time? Because Einstein tells us that gravity is a warp, it's a bend, it's a curve in space-time. Okay, so if gravity is a curve in space-time, how does this graviton warp the fabric of space-time? Move it, pull it around. Well, that's almost like, I can hardly wait to hear what they have to say for that. I'm sure there's going to be another invisible field that nobody can see or measure, that reaches up and pulls space-time around. So there's these problems. And rather than say, well, maybe we've got so many problems and we keep adding new assumptions with these new particles, maybe we ought to look at it from a different viewpoint and see if we can't, produce a different model that explains the data more simply, so that we get, a Newtonian gravitational model with nice, neat little ellipses, everything, all the planets going around the sun. And oh, that feels so much better. That's probably to be more likely the way it is, rather than, this hodgepodge of, 14 dimensions in string theory and 38 particles or something like that. And, everyone's an assumption. So that's kind of my problem with this dogma in physics, is that they're creating models to fit data. Well, so did Ptolemy's crew. They created models to fit data. It's just that the models weren't very good. There were simpler models, more elegant models that one could create. And Brian has come up with some very elegant models. So looking forward to seeing his next one's going to be about gravity. But so they have problems like this. So our particle theory, our inability to see that psi, even though it's even in our laws, that we refuse to think it exists, even though it's been demonstrated thousands of times, and people still say, well, nobody's ever actually done a real psi experiment with real science and so on. Of course they have. It's been done thousands of times. And it just doesn't make any difference because it conflicts with belief. And the speed of light, it's supposed to be a constant. Well, it is a constant in practical, I would call it a constant because it is a practical constant. But theoretically, it could change. Theoretically, we can even see how it could dramatically change and end up being our bars of our playpen and other things, you see. So with a little more openness and a little more creativity in their thinking, there's various ways to approach these problems that give us answers of, well, why does the speed of light seem to be a constant? Well, why change the delta t and the delta v, the pixel of volume? That's not something you're going to change. Well, that's why it's going to be a constant, because the delta t and the delta v ought to be constants, but that doesn't say you can't change the number, the value of that constant from time to time for various reasons. You just need a bigger picture instead of this physical reality is all there is and everything that exists must be a derivative of physical reality. We get that, and that's, we've never progressed past Newton. So Newton, the universe was a big clockworks. If you knew all the states of all the particles at any one instance, you could calculate everything else that would ever happen. You see, that's where our determinism comes from. We got to Newton, we understood him, and then we ended up with relativity and quantum mechanics, and everybody's mind is still based solidly in Newtonian worldview. We've never progressed past it. When we found out that particles were probability distributions, actually they weren't really particles. There are no particles. There's probability distributions which materialize into particles when we measure them. And instead of saying, well, that conflicts with our belief, let's make up something else that sounds better. They, instead of opening their mind to see it maybe from a different way, they just keep making up stuff that props up their beliefs and makes them feel better. That's unfortunate, but our science has gone that way in the last 100 years. And there's another thing that I just read the other day. They said there's kind of an astounding anomalous fact about physics that I didn't know about. And I just read this, and so I don't even know that it's true, but I read it. And what they said was that there hasn't been any time in the last several hundred years where we have had what did they say, like a 7 or 8 decades, or maybe even 8 or 9 decades without any major fundamental advances in physics. We have been dead in the water for longer than has ever happened before since kind of the beginning of physics, which doesn't go back that far. But anyway, we're in a dead zone here. Oh, we found lots of little new things, but finding a new particle isn't what they mean. That's not a fundamental advance, but a fundamental understanding of reality, that the way things work hasn't happened for a long time. And why have we had this dead zone? Because physics and science in general has gotten into a dogma, a belief space, where their Newtonian worldview doesn't work anymore, and they're shoehorning everything into that viewpoint, and where they just can't do it and it doesn't fit, well, geez, that's the hard problem. Oh, geez, that's the thing that nobody will ever understand, you see, and go on. So that's the problem. Instead of saying, this is a problem, okay, it's a hard problem. Maybe we're looking at it the wrong way, you see. Maybe we need another that don't do that. So because of this belief trap that they're in, they have painted themselves into a corner in which the solution doesn't exist. So they can only see, what their belief allows them to see, and the solution doesn't fit. So it's like the Newtonian mind has basically refused to go beyond Newton's worldview, and we're still, everything is physical, it's all deterministic, it's, so you have quantum mechanics that says, well, it's not that way, They're probability distributions. Oh, that's just the math. We just pretend they're probability distributions because that works in the math, and we don't know what it means, and we'll never know what it means. You see, and we'll just make up another particle. We measured something, and we'll just add another row or another column to the standard model, and here we are. Gravitons, yeah, well, they must be out there somewhere. We just can't find them. Probably find out they're an invisible particle that nobody will ever be able to tell or see, but they're there. Trust me. This is the problem. My thought. This is the problem that physicists are having, and why we haven't found anything fundamental new about reality. We're just chipping out little bits and pieces, and that's not what they meant. But there hasn't been any fundamental new discoveries about the nature of reality for a long time, and that's because we're in this belief box and can't get out of the box. Consciousness is the computer, Dr. Fredkin. Okay, you've been up against that wall for what? in 1990 something is when Fredkin published that. He's been saying other. Well, here it is 2013 or 2012, and I heard him on a panel. Same thing. It's in other, but he's not gotten past that point. And I think he believes that it's impossible to get past that point. Just like Feynman said, it's impossible to know why these things happen this way. It's just impossible. What he meant was it's impossible to put it into a Newtonian viewpoint. It's impossible to make it physical. It's impossible to have it be a matter, a particle thing, instead of having these woo-woo waves and probability distributions. That's what's impossible, but we're going to stick with it. That's our story, and we're sticking with it. That's kind of the way they have been.
Well, they haven't read My Big Toe. That's the first fundamental shift in physics.
Yeah, I don't think they will read My Big Toe. I think they take one look at it and say, oh, this is woo-woo nonsense, and throw it out because it doesn't fit their belief, just like they throw out Pear Labs. And that's got a lot more credibility than My Big Toe, because there's a whole bunch of physicists, not like one guy, there's a whole bunch of physicists at Princeton saying, hey guys, this is real. And the main group of physicists say, impossible, can't be, so we're not even going to look at it because we know just basically that it just has to be wrong. You guys have made a mistake someplace, and we don't have the time really to help you out. It's that kind of an attitude.
Well, I think eventually it will be accepted. There's one thing that you mentioned, gravity, and gravity is also a constant, which Dr. Sheldrake did some research on as well and found that there was as much as a 1.3% variation in that. Can you comment on what the implications of that might be?
Well, gravity is a harder one because, we measure the gravitational pull here because we are small things on the surface of a big thing, the Earth. And from Newton's view, masses attract. Of course, we can't find anything physical why that ought to be. Why should masses attract each other? And nobody really knows. So there's this gravitational force, which is almost a mystical force because it just happens, and there's no real theory of why it ought to happen, why masses ought to attract each other. But we just say that it does, and it seems to work out that way because using that theory, we can derive all the orbits, of the planets, and we can launch satellites that orbit Saturn and then drop down on a Saturn moon. And if we didn't have a really good practical understanding of gravity, we couldn't do all those things. But every mass is supposed to attract every other mass. So our gravitational experience here, what we measure as a gravitational field, is a result of every mass in the universe has some tiny input to it, you see? And as those things all change around, those tiny inputs might change too. Well, all the stuff that's far away has such a tiny, tiny, tiny effect that it doesn't matter too much to us. But gravity's not this simple thing. If you want to measure gravity in a universe that has billions of chunks of mass in it, and every one of them is attracting every other one, you have a very complicated problem. So we're always approximating what the gravitational field is, and as things change around, it's changing out there in far decimal places. So that could be some of it. It's not constant. Everything that's measured depends on the tools that you use and the theory with which you go about measuring it. So now that's in the small stuff. As far as the big stuff goes, gravity, just like, we talk about this is a simulation. So at the highest level, the most simple explanation is that it's just calculated. It's part of a calculation. Okay, now this calculation, as Brian Whitworth describes it, is really a process, which isn't surprising because, this is a process fractal. It's all about processes. So it's not necessarily like an equation that's being solved, as it is a process at the basic level of computation. At the ones and zeros level of computation, there's processes that are going on that does this computation. Now, Brian Whitworth is going to say that it's a phase. Gravity has to do with the phase of motion of processing in his four-dimensional grid. He's got the process kind of down for what creates all these particles, and he's going to have another paper after he publishes this one that'll talk about gravitation. So he's done force and light and mass. Mass is basically a lot of processing that's going on. So he has reduced all of physics to a computer problem, basically to ones and zeros of computer processing, you see, and that's just another view. You don't need all the particle theory, but you can derive the same equations. You can derive E equals m squared and the rest of it. So the equations come out the same, but it's a different theory, and one that has several assumptions rather than 38 assumptions or 14 assumptions. It's got like 2 assumptions or 3 assumptions, that sort of thing. So it's getting people to get rid of their belief and see that bigger picture. So how could gravity change? Well, gravity is just, a calculation. We talk about, a computer. This is a virtual reality and it's computed in a computer. Well, how do you get gravity in The Sims? The Sims people don't float around. Sims people, well, that's a virtual reality, right? In the World of Warcraft, a virtual reality. Those people don't float around. They have gravity. Where does their gravity come from? It's part of their rule set, right? It's just computed. It's a calculated value of the way that works. Now, Brian will tell us that that the way it's calculated is that it's part of a process, at the quantum level is how the calculation is done. But it really doesn't matter. We can just say all of that's just, it's a quantum computer. See, Brian's computer is a quantum computer. And it's a computer and it's calculating. And gravity is an effect of the calculation. You don't have to have a graviton. All you need is a computer. This is a virtual reality. You don't need a physical process. So if you were a Sims character and you were a scientist and you happened to be conscious, you were a conscious Sims character and you were a scientist and you wanted to figure out where gravity came from, because everybody walks around and seems to be attached to the ground, and when the Sims people drop things, it falls down, and when they jump, they go up and come back down again. Well, they could, with a little experimentation, come up with Newton's laws. They could come up with with gravity. But now if they started saying there's particles, see, there's gravitons, and it's this graviton, is an invisible particle with an invisible force field, well, that's just them making up stuff. That's sort of like the heavenly bodies go through the heavens because they're pushed by angels. That's just an explanation, and it takes a whole lot of assumptions to back it up. Where do the angels come from? Where do they live? What do they eat? How fast do they fly? Those wings, what are the wings beating against? Well, you have to keep making up assumptions to prop that theory up. And pretty soon, your theory of angels pushing the heavenly bodies around will work if you have 30, 40 assumptions to prop it up. That's that's a problem. Actually, I heard Feynman give that example in one of his lectures. He gave this lecture. This was Feynman of quantum mechanics fame, and he was giving a lecture. He wrote wonderful introductory physics books. Introductory, not for the layman, but introductory for physics majors, for college freshmen and sophomores. And in that lecture, he used this model of pushing the heavenly bodies around by angels. And he said, what's wrong with that theory? And some people said, it's ridiculous. That's what's wrong with it. And he said, no, that's not what's wrong with it. You don't judge something because you believe it to be ridiculous. That's your belief. He says, it doesn't work well because there's too many assumptions. That's what's wrong with it, you see? Well, Feynman was a very brilliant man, and that's right. So I've kind of used that example. I use it in my book. But the only problem with that theory is it uses so many assumptions that you just can't give it a whole lot of credibility. Well, same with the Standard Model, same with the string theory. They've got so many assumptions now that they're beginning to lose credibility because we're looking for something that's simple. And one of the guys, did you watch that video on YouTube where they had the 5 scientists talking about virtual reality?
That was called Rebooting the Cosmos.
Yeah, Rebooting the Cosmos. And you notice there was one physicist from Europe, Jürgen, and he made the point that he says, when we figure this out, when we figure out how this virtual reality really works, he said, it's going to be simple. It's going to be very simple. It's not going to have a big complicated mathematical description. It probably won't even need mathematics to describe. It's going to be just a couple of things that are really simple, will make everything else make sense. But of course, Jürgen didn't have any idea what that might be. But he knew that something complex, if it takes 10 sheets of paper of mathematics to present it, if it takes 14 dimensions and 38 particles, it's probably not it. It's going to be simple, guys, and that's, it's not even going to need the mathematics. And when I heard that, I kind of put my hand in the air and said, right, that's exactly the way it's going to be. It's going to be simple, like consciousness is the computer. This is a virtual reality. All you need is the assumption of consciousness exists and evolution is a process, that exists, and the rest of it just falls out with a little elementary logic. It's going to be simple. You don't have to write a lot of equations. So it's like, well, where are your equations, to show that this is the way it is, and you're missing the point. If I had a lot of equations to demonstrate this, then it probably wouldn't be the right answer. You see, that's the point. So Jürgen was exactly right, and he's doing this all from like two assumptions. There's this four-dimensional grid, and there's this processing that goes on. He calls it a Planck program. That's it. Everything else falls out of that. And Brian's stuff is not full of math. He's just telling you how it is. My stuff's not full of math. Brian has taken it from the bottoms up. He started with how the computer works. How does the computer do its computations? How does the computer work to create this virtual reality we call, our universe? And I start from the other end, which, consciousness. Start with the consciousness system, and then, he has where we meet at the boundary, where his boundary kind of moves up and has these kind of bigger pictures, like it's a virtual reality and it has these properties and so on. And where my model comes down and meets at the how does the physical virtual reality work, we both see the exact same things. What Brian sees at the interface and what I see at the interface are identical. But he started from the bottom and worked his way up, calculating in his quantum computer of how the processes create physical reality. I start from the top with consciousness and work my way down to this being a virtual reality and why, and we see the exact same things. So that gives me a lot of good feeling. You see, there's another guy, totally independent, coming from the opposite direction, and where we meet at that boundary, we see the same things. So I think that gives Brian a little confidence too, because, it's not just him alone in the world, or me alone in the world. And now we're starting to get more confidence because now there's a whole panel full of physicists that come from, expensive educations and high-level institutions. And they're saying, yeah, this virtual reality idea, it works. It's the only thing that's going to work. And then you finally get one of them to stand up and say, and it's going to be simple. Probably won't need any math. It's just we need the right concepts, you see. And here Brian's got it from one end, I've got it from the other, and it's like, guys, here we are. Come take a look. But of course, that's probably not going to happen for a long time because we hardly exist. We're not, Brian and I, neither one of us can really get on the map of traditional science because we're outside the beliefs. And even people who say, yeah, it must be a virtual reality, but somehow, I don't know how, but somehow it must have computed itself because otherwise my beliefs are wrong. You see, so you still have a lot of that. It's a slow process.
Well, Jürgen said something very interesting as well on this rebooting the cosmos thing. It, of course, was all about virtual reality. He said the kids will get it because they understand the workings of the video games.
Yeah.
And they'll get it first.
Yeah.
So here's to the youth.
That reality is virtual is not such a huge leap out of the box. For the older people who don't see that, the virtual reality is a big step out of the box. And that the next higher relativity, that physical and non-physical are not fundamental. It's just depends on the observer. So to say that something is non-physical isn't like you've given up the woo-woo science and craziness. It just means that you understand that reality from a bigger picture. There is no physical and non-physical. We're no more physical than we are non-physical. It's just because we're here, we appear to be physical. That's the way virtual realities are. When you're a Sims character, the Sims world appears to be physical. When you're an elf running around in World of Warcraft, that World of Warcraft world appears to be physical. If you run into a tree, you bounce off, just like you would here. So it's because they have rule sets, and the rule sets give you the sense of being physical, because the rule set basically defines the action, the energy exchange. So every virtual reality has its rule set, and the beings in that virtual reality find it to be physical. But when we look at the Sims sitting outside on our computer model, we don't think that the Sims is physical. Well, that's not physical. That's just on my computer. That's just information. And we don't realize that the same is true of us. It's just information. We just happen to be inside a higher order, virtual reality. So that's the big step. And I think you're right. I think the kids coming up who will have virtual reality kind of in their blood by the time they get into being physicists and things like that, they won't find that step out of the sandbox to be so huge and scary. They'll say, wow, neat idea. We're in a virtual reality. I dig it. They will like that. So I think times are coming, and maybe they're only 20 or 30 or 40 years away when we, I know some famous guy said, how you change fundamental theories in physics? You wait for the older physicists to die. I can't remember who said something like that, but there's a term that says what you have to do is wait for the old guard to turn over. And that then gives you a better chance at seeing a different picture, because as long as physics is stuck in that belief box, there isn't going to be a solution, and that long dry spell is going to keep on keeping on being dry. That's kind of where we are. But I think we're kind of on the cusp of doing better, because we do have a whole new generation coming up that see virtual reality as not all that far out. And we have even a lot of physicists now that are the old guys, in positions of authority, like this panel. And they're saying virtual reality, although they still are stuck with nowhere to go. What's other? Fredkin's been stuck with other for 25 years now, hadn't gotten by it. And this other guy thinks it must compute itself. And Jürgen was the only one who really had a good grip on that. And he said, it's going to be simple. It's just not going to be a big mathematical thing, guys. It's just going to be a simple concept. That's so we are getting there. It's starting to turn. But now Jürgen's probably 1 or 2 or 3 out of tens of thousands. So it's still very much in the margins. Rupert Sheldrake is absolutely correct. And there was a few more of these dogmas of science that he didn't put on his list that need to go there too, like the standard model, particle physics. And they all boil down, though, to the same belief blindness. So you have 10 of them or 11 or 12 of these pieces of dogma, but mostly they boil down to the same logical problem, and that is physical reality is all the reality is. It's the only thing that exists, and everything that exists is a causal result of physical process. And that's the kind of the one big belief that is driving most of the rest of it. They just can't see that there may be any other way to do business. So with a virtual reality, like we just talked about, speed of light can change. It's just a number in a computer. It's an input value. The larger consciousness system is running this, and it has input values. What do you want your refresh rate to be? Well, I don't know. How much throughput can you stand? About this much? All right, let's make it about 10 to the minus 44 seconds. That ought to be okay. Sure, run. And when it comes time to change it for whatever the reason is, because we need more resolution or because we're grown up enough now that we can get out of the playpen or whatever, it can change. But meanwhile, it doesn't change very often or very much. And the system tries, when it changes things, it tries to keep it as constant as it can within the fact that it has to choose from discrete numbers and can't always make it come out exactly right. So I don't know, it just seems that these ideas seem to explain so much with so few assumptions that you kind of end up shaking your head and saying, you know, come on, guys, you know, give us a chance, you know, give us a look and see what's here. But we got to get through that belief barrier first. And that's what, you know, that's why we make these videos, right? That helps us get through the belief barrier. But Rupert Sheldrake is one of the people who's trying hard to break down those belief barriers, and you know, my hat's off to him. He's doing a very good job of it. Although I understand his TED Talk got edited, and he got edited, I suspect, because he got outside of the beliefs that are acceptable.
There's a whole explanation as to why it was removed from the TED Talks list, and then there is Dr. Sheldrake responds to it, and TED Talks claimed that they didn't want to put into a science category something that appeared to them as pseudoscience. So they've listed it and placed it somewhere else on a blog that TED Talk has, and that was the reason.
Yeah, well, that's exactly what I said. It's because it conflicted with the belief. He ran afoul of the very dogmas that he was talking about. The block of of the traditional physicists there said, this is nonsense. This is pseudoscience. That's not real science because it disagrees with our beliefs. Well, of course, they don't say our beliefs. They say our fund says that this cannot be true. Therefore, it isn't. Well, it's their beliefs. So that's what happens. You see, that's what happens to Pear Labs. Pear Labs has this, and they get the cold shoulder. Nobody will publish their documents because, not because their science isn't good, but because their science conflicts with physics dogma, with physics belief. So they don't get to publish, and the Sheldrakes get their stuff put under pseudoscience and whatever. So that's kind of what we're up against. But time will help us. Again, a decade ago when I published these books, you couldn't find a scientist outside of Fredkin who would stand up and say virtual reality without also saying, oh, that's pseudoscience, baloney, only fools would think that, and so on. And Fredkin evidently got a lot of that from what he said at that meeting. He went for a long time when nobody would take him seriously. And now he's on a panel, you see, of something being taken seriously. So there are changes. It's moving in the right direction, but true believers, trying to move them off their belief center, out of their belief trap, is a slow business. I've always thought, I started when I first published My Big Toe, I sent it around to a lot of the top consciousness researchers and some of the physics people, and basically it got the same kind of welcome as the Sheldrakes did on TED. It never got read, never got looked at, and I came to the conclusion that you don't work this problem from the top down. You don't go to the existing experts and people that are the top of the field of, say, consciousness research and so on. That's not where the answer is going to come. Those people have a vested interest in keeping it just the way it is because they're top dogs in this field under the current assumptions, and they don't want any other things than that. And everything else is bogus and pseudoscience. They're going to squirm and fight. They don't, they're not interested. They don't have time. They're too busy. And so on, that the only way this will eventually work out is from the bottoms up. So then I gave up on all of that, trying to appeal to people who were scientists or conscious researchers, and I said, let's take it to the people. Let's just, eventually the scientists will be drugged, kicking and screaming, to the truth, into the future. But it's going to be drugged, kicking and screaming by the rest of the people. They will eventually change their minds, but it won't be quick and it won't be easy. And top down doesn't work. It's got to be bottoms up. So that's why we make these videos. And that's why, Rupert Sheldrake gets up and does TED Talks, even though he gets put in the pseudoscience box. He does TED Talks. And I think that's the solution, is from the bottom up. Once once a lot of people get it, then more of the young people going into science will get it. They'll come with that. They will have looked at the videos and seen these opposite viewpoints, and they won't be quite so hard over when they ask Feynman, well, why does it work this way, Dr. Feynman? And he says, shut up and calculate. They won't take that. They'll say, well, there's some alternatives. And it'll start to break open. But I see the young people as the key here in change. New people, younger people who can get out of the box. But yeah, the TED Talks have to be politically correct. And it's a political correctness within science. It means you stay within the beliefs of science. So it's a shame, because the whole idea of TED Talks was to get that most interesting, most exciting, current edge on the cutting edge information out there to people, and then they turn around and say, well, if it doesn't support the status quo, we're not interested. So we only really want cutting edge information that supports the status quo, which means they really don't want any cutting edge information at all. They want stuff that sounds good to the status quo. So started out with a good idea, but like most things, given a little time to mature, it turns out to be a lot less than it initially started out to do.
Well, thank you, Tom, for shedding light on the variations in the speed of light and our purpose and our direction here, and let's hope it catches on. And thank you to all the true scientists who continue to pursue the truth and know that the answer is simple. Just keep looking.
Yeah, stop beating that dead horse, right? And start looking somewhere else.
Thanks, Tom.
You're welcome. Thank you, Don. It's been fun as usual.
Thank you. Fascinating.